Remember all of your stretches, compressions, reflections, translating left, right, up and down, all of that from grade 12. So everything that is multiplied, the A and the B, those will be always stretches and compressions. A new word for stretches and compressions here, dilatations. You ever heard the word dilated? They use it sometimes for eyes. It's like your eyes or really, really small little pupils are really big. So that means getting things bigger and getting things smaller.
Sorry for the interruption. Any student, whatever grade you are in, 9, 10, 11, or 12, any student who has not had their picture taken, please go to the gymnasium and have your picture taken. You don't have to purchase pictures. It's free of charge to get a picture taken, and you will also receive a student card, and you must have your picture taken. So if you have not already, please go to the gym to do that. Thank you.
Perfect. Anybody not had their picture yet? You can go down and get that done right away. So the reason transformations are so nice is that you can graph a lot of things if you know what a basic graph looks like. Like we know, or hopefully you know what a basic x squared graph looks like. Well, then this minus outside would be a vertical reflection, and the 2 would be a vertical stretch. Finally, the minus 2 would move things 2 to the right. Do you remember that all of your horizontal things were sort of opposite of what you saw? When you see a minus 2 inside the function, it moved it 2 to the right. You saw multiplication by 2 inside the function. It was actually multiplication by a half. Everything inside the function was different. So we could, like, it's going to be fine if you just graph the final graph. But here you have your basic graph, x squared. It has very easy key points. On your basic graph. An x squared graph, it's going to be really important to figure out what happens to 0, 0. And there's different ways. Some people do a chart. I like to just, I'll actually make this orange in the end, because that's my final graph. I'll make my final point. Wow. Doesn't it look like it's orange? There's something messed up going on with the smartboard, because I'm pretty sure that looks orange to me. Not a dotted black line. This one. I want it orange. I want it like this. Say it again. Oh, now it's orange. Okay. So what I like to do is I like to go, okay, the minus 2, that's going to multiply my y values are going to get multiplied by negative 2. And then what's going to happen, I'm going 2 to the right. You can do your mental math. I know you might have done it a little bit different way, but saying what happens to 0, 0? Well, after multiplying my y by negative 2, it'd still be 0, 0. But then if I move 2 to the right, on my orange graph, it's 2, 0. And sure enough, I have the point 2, 0. If I wanted to find out what happens to another point, I could take 1, 1. Multiply my y value by negative 2, would go to 1, negative 2, and then moving 2 to the right would take me to 3, negative 2, and sure enough, that shows up on my graph. So I can look at specific points. Then I wouldn't have to draw the blue and the green graph. And I know how much you guys love drawing graphs. So you probably wanted to draw all of the extra graphs, I understand. But if by chance you're one of those people who doesn't like to graph a lot of things, that's really rare, and you just wanted to graph the final one, that's perfectly fine. So here we have g of x is 2 minus x. Something from grade 12. If you want to use your transformations, you have to write horizontal stretches and horizontal translations in factored form. So probably you're used to, first of all, you're probably used to that first. Negative x plus 2, rather than 2 minus x. You're used to the x coming first and the 2 coming second. Then the number one mistake that happens in transformations in this situation is people see the plus 2 and they think, oh, x's is always opposite, x's are liars, so I want to go 2 to the left. But in this situation, before we can do that, we have to write it in factored form, and this actually is moving 2 to the right. You're going to have a horizontal reflection, then a horizontal translation 2 to the right, and finally a vertical translation 3 units down. So if I took my green graph and I reflected it, I would get my blue graph, and then I can move it 2 to the right and 3 down. So that factoring step is important if you're using transformations. Question for you is, does anybody remember the second method that you learned in grade 12 for graphing this? Once I show it to you, you'll be like, oh yeah, I remember. But when I just ask you that question, do you remember a second method for graphing this? The second method for graphing this, just this part, I'll just graph this part, would be to first graph the inside. So 2 minus x, that is a slope of -1, a y-intercept of 2, y-intercept of 2, slope this is the graph of 2 minus x, or negative x plus 2. Much easier to see when I write negative x plus 2, because then you can see the slope and the y-intercept. There's your regular line. The second method that you learned in grade 12 is you can square root any function. And when you square root any function, there are 2 points that never change. They are 0 when y is 0 and when y is 1. Because square rooting 0 and square rooting 1 result in the same answer. But then, anything that you square root between the y values of 0 and 1, that's the only time when you square root something that the answer gets a little bit bigger. Right? The square root, it's kind of cool. Right? If I square root 1/4, I get 1/2, and 1/2 is bigger than 1/4 was. Graphically, that means that purple graph is a little bit higher than the blue graph was originally. Then after that, when you square root, like square root of 4 is obviously going to get smaller, square root of 2 gets smaller. So this was another technique. So I could have graphed the green one here first, and then if I move this graph down 3, it would match up perfectly with our other graph as well. So just a reminder of that second technique. Most often though, this second technique was when you were asked to square root, like if I said, hey, I'd like you to graph the square root of log of x plus 3. right? But you could draw a log of x plus 3 and then square root that afterwards. So again, at the end of page 22, notice there's some practice listed. That is stuff out of your textbook that you can do. Take your textbook home. There are a lot of really good questions in there. In your textbook as well, there are, sometimes there's green boxes of AP style questions. Those are really good ones for practice. And they're often, if I find good ones like that, I've listed it in the homework as well. So a function is called one-to-one if each x in its domain has exactly one image in its range, and each y in its range is the image of exactly one x in the domain. Graphically, this passes both the vertical and horizontal line tests. We use the vertical line test to see if something's a function, right? You draw a vertical line across a graph. As long as it hits one point, you can say it's a function. For something to be one-to-one, it also has to pass a horizontal line test. Because when we get to inverses, in inverses you switch x and y. So if something doesn't pass a horizontal line test in the original one, when you switch x and y, horizontal lines become vertical lines, and then it won't pass a vertical line, and your inverse won't be a function. You can still find the inverse, but your inverse will be a relation and not a function. So the idea of something being one-to-one is nice because then it makes your inverse a function as well. So are these ones one-to-one? Does each x go only to one y? And vice versa, does each y related only to one x? Yes. So this one is one-to-one. The second one here is a function. Each x only goes to one place. But going backwards, this y value has 2. So then it's not a one-to-one function. Does anybody know what the second function is? Look at the numbers. What do you think is happening?
Parabola.
It's a parabola. It's just x squared. Does it make sense that a parabola does not pass the horizontal line test? It's a function, passes the vertical line test, but it doesn't pass the horizontal line test. Our regular graphs that don't pass the horizontal line test make us make special rules for inverses. What's the opposite of squaring? Square rooting, right? Is your square root graph a perfect flip of your parabola? They just ignore half of it, right? Like that's caused you all sorts of problems in high school already. Has anyone not lost a half a mark for the plus or minus in their high school career? Have you all successfully earned that negative 0.5? Successfully earned the negative 0.5. I don't know if that's sounds like not the right sentence. I've successfully lost marks. Right? I guess you successfully lose marks if in the process of losing marks you have learned something over time, then that is a good thing. That's part of that would be successfully losing marks. Unsuccessfully losing marks is where you lose marks and haven't learned anything from it. That would be unsuccessfully losing marks. So we use the horizontal line test. And the graph of a function represents a one-to-one function if and only if every horizontal line intersects the graph at most one point. And this is one of my favorite sentences in math. If and only if It actually comes up enough in higher level maths that they have an abbreviation for it. The abbreviation for if and only if is if. If and only if. I don't suggest starting to use that in talking wise. You can go there if you do this first. But, that's a fun one. Does anyone know what this stands for? That's a fun one too. This means for all. Anyways.
Why?
Why? I think for most of these things is inherently that mathematicians are lazy. Okay? Like if and only if, that would take me at least a second and a half to write out. And it's like 4 words, and as a mathematician, I don't like writing words. So if I write if with 2 F's, it is now only 1 word and only 3 letters. Oh, I'm so much more efficient. I just saved a second of my life. Same thing like for all, that's like 6 letters. Why don't I make an upside down A? Right? Like X belongs to the real numbers. Oh, let's make that belongs to, or is an element of, so we don't have to write a whole bunch of words. And real numbers, let's just make it R funny. You're doing some of these math things already by making things shorter, which seems really efficient. What's the problem with getting efficient? Is that it hurts our brains and we don't understand what's going on at a start, right? How many people, when they saw this at the beginning, are like, what the heck? What's going on, right? And now you're comfortable with it. You're like, oh yeah, no problem. X is everything. But I don't want to write out X is everything. Sorry. So determine if the following functions are 1-to-1. What graph is this? You recognize it? X cubed. Is it 1-to-1? Absolutely. What's the second graph look like? It looks like sine. Is it exactly sine? It looks like some sort of, might not be perfectly sine, but is it? Doesn't pass the horizontal line test. That's why we have problems with sine inverse. You might not have realized you had problems with sine inverse, but in grade 12 we couldn't just rely on our calculator to find answers. You had to also know a cast rule, and you had to know like where things were positive and negative to write down all the answers. It was a little bit more complicated. You couldn't just type in your calculator and go sine inverse of 0.5 and say, it would just come up as pi over 6. Or 30 degrees, depending on what your calculator was in. It didn't tell you all the answers. We had to do extra work to find all the answers. That's because it's not 1-to-1, and in order for our calculator to work, we have to create special rules. Because technically, if I do sine inverse of a half, and I draw a vertical line and a half, how many times does it intersect the sine graph forever? Infinite amount of times. And if we taught our calculator to tell us all the answers, it would have to start putting out an infinite amount of answers, and your screen would just start like going through answers and be like, what do I write down? What do I write down? We have a problem. So we want our calculators to function, so we make inverse functions, but in order to make an inverse function, it has to pass both the vertical and horizontal line tests. So if it's a 1-to-1 function, then the inverse function we write like this, okay? And all our French people are thinking of inverse as reciproque, right? This is one of those weird words where the direct translation screws up completely. Right? And we learned in grade 12 with inverse functions, we can just find them by switching x and y. So here's the function, all we have to
the
do.
interruption, but all
students that have not had their picture taken, this is your final call for pictures. Staff and students, please go to the gym to get your picture taken. That's all students and staff who have not had their picture taken. Go to the gym.
So we just take our x coordinate and y coordinates and switch them, and we have our inverses. So our domain of our original function becomes the range of our inverse, and our domain of our inverse becomes the range of our original function. And the graph of a one-to-one function, f, and the graph of its inverse are symmetrical over the line y equals x. So if you have the line y equals x, which is this diagonal line, if you wanted to find the inverse of something, you just need to reflect it over that line. So if I took a horizontal line, y equals 3, if I reflect it over this line, x and y switch, it would get x equals 3. Horizontal lines would become vertical lines, and that's a perfect reflection over that diagonal line. So we say that it's symmetric with respect to the line y equals x. So sketch each of these functions and their inverses. So I have y equals the square root of x plus 2, which is just your square root graph moved up 2. That's the original one in black. Its inverse is blue, and all I did to find the blue graph was I took all of my x coordinates and y coordinates, all my coordinates, and just split them, right? I had 0, 2, now I have 2, 0. I have 3, 1, now I have 1, 3. Or I had 1, 3, now I have 3, 1. And I know you remember this, but algebraically, if you wanted to solve, you'd switch x and y, and then you solve for y. Now what would happen here? Well, I would get the square root of y by itself by moving the 2 over. You're okay with that? If I just switch the sides, so y is going to be on the left. But I move the 2 over to get x minus 2. And then to get rid of the square root, you would have to square. But in solving it algebraically, I get a parabola. Solving it graphically, is my blue graph a parabola? Well, it's half of a parabola. We have a restriction on this parabola that your x values has to be bigger than or equal to 2. Because there was a restriction on my square root graph. Can you see that the range of this square root graph is y is bigger than or equal to 2? And if there's a restriction on your range, there's going to be a restriction on your domain of your inverse. But this would be a very typical mistake to make. Just solving, switching x and y and solving, and not taking into consideration original domains and ranges. So that's like that fine detail that the AP is like, oh, the AP likes fine details. That's like, they have to decide who in this course gets a 5, a 4, a 3, a 2, and a 1. And so a lot of the multiple choice questions that are out there are like fine detail questions. If you make enough mistakes in your fine detail, it drops you from getting a 5 to a 4 or a 4 to a 3. So what we're going to try to do is when we're reviewing things, help point out some of those fine details again. They make sense, but they're easy to forget. X minus 2 cubed, if you graph that one originally, that would be your x cubed graph. Move 2 units to the right. Switch all of your x and y's. And there's your inverse graph. Technically, that blue graph, if I wanted to find its equation, I could switch x and y. Cube root both sides. And this is the cube root of x plus 2. That's the equation of that blue graph, algebraically. There's no restrictions on my domain or range in my black graph, so there would be no restrictions on my domain and range of that blue graph. On the previous graph, did I go too quick? On how I switched from, you're gonna let me know. Sometimes I get excited about the next math that we're gonna be learning. I'm like, ooh, I wanna teach you more, I wanna teach you more, and then I go too fast. So you'll let me know, right? Okay. Because I know, especially these graph ones, they take a while to label everything. So I know technically your first take-home quiz says Wednesday here. I said I would accept it tomorrow. So if you're not done, but once you are done, you can hand it in here. Have you guys started a group chat already? But you have your your peeps that you know who to go to and stuff like that. All right. So, if you have a one-to-one function, then the following thing is true with composition of functions. In fact, this can sometimes be used to prove two things are inverses. F inverse composition f of x should get you x. And this should kind of make sense. I'll do a really simple example. I'm going to just take a straight line. I'm going to make one equation. I'm going to make my f of x, x plus 3. Then if I wanted to find my inverse, I would switch x and y. Oops, that's not switching. Let's try that. That's right. F of x is equal to x plus 3. So if I switched x and y, I'd have x equals y plus 3. Really easy to solve for y. I just have to subtract 3 to the other side. Does it make sense that your inverse would be x? Oops. Inverse of x would be x minus 3. I would undo what you did to begin with. So when you have the composition of functions, f inverse of f, or f inverse, what it's saying is you're putting into one function first, whatever answer you get that comes out goes back into the other function. So in my situation here, if I wanted to find f of f, no, I'll start with f. I wanted to do f inverse of f of 3. Well, what does this mean? This means I'm going to plug in 3 into f of x, and I get 6. Then 6 goes into f inverse, and I undo what I just did, and I get 3 back again. If an inverse undoes the other one, that's what they're for, right? They're the opposite thing. Adding 3, what's the opposite? Subtracting 3. All day we could have fun with like, okay, I'm going to give you a number. I'd like you to add 3. I'm going to get subtract 3. Magic. Did you get the number you started with? You'd be like, that is not magic, Mr. Jarrett. That's just simple math. But that's always going to be the case. Doesn't it make sense that if you do something and then you then say, let's undo what we just did, you should get back to where you started with. And that's what this notation is saying. And it's actually a way to prove inverses. So in grade 12, this wouldn't have said use the theorem above, but in grade 12, you would have been asked, show is 1 over x plus 1 the inverse to 1 over x minus 1. And what you would have done is you would have switched x and y, found the inverse, and if it matched up, you would have said, yes, this is true. But now we have a new technique that we can use. We can use the composition of functions to show and see if we get x. So if I do f inverse of f of x, that means I'm going to plug in f of x, which is 1 over x minus 1, in for x in f inverse. And I get 1 over x minus 1 plus 1, which this is dividing by a fraction, multiplied by the reciprocal, and I get x minus 1 plus 1, and I get x. So part 1 of the theorem works. Plugging f of x into f inverse made it just equal to x. Then I also have to check f of f inverse of x. So now I'm going to take the f inverse of x and plug it in where the x was. So that's, I'll put it in brackets here. This is my f of x, f inverse of x, and that's being plugged into f of x. And the 1 and the minus 1 cancel out. I get 1 over x, and I get x as well. Both of them work with some restrictions. The first one works as long as x is not equal to 1. The second one works as long as x is not equal to 0. But this would verify that they are inverses of each other with 1 point sort of, or 2 values somewhat being problematic. Okay? Here is, like, sorry, I'm having fun little details. And again, I said those little details can sometimes catch you up. First of all, the opposite of squaring is square rooting. So it's quite typical to say the inverse of x squared is the square root of x. Technically, that's a little bit of a problem, because if you took the whole parabola and switched x and y's, you would get a sideways parabola, but the inverse is only part of it. And if I would do, just for fun, to prove that this is not quite perfectly the inverse, so if f of x is x squared, and g of x is the square root of x, and I ask if they're inverses, then I could say, what is f of g of x, and what is g of f of x? And if they're both equal to x, then we could say they're inverses. F of g of x would be, g of x is square root of x. This would be the square root of x all squared, and the square root of x all squared would be x. G of f of x would be g of x squared. And by the way, this would have a restriction, right? X would have to be bigger than or equal to 0. This would be g of x squared. G of x squared is the square root of x squared, which is absolute value of x, not x. Close, but not exactly the same. So generally we do say that the square root of x is the inverse of x squared, but it has restrictions on it. And that's where all that plus or minus caused you problems in the past. And the square root of x is just a positive number and never a negative number, which sometimes caused problems in the past. And now that we're in calculus, we're getting into some of those details and a little bit more of those details, because here everything works. Here it only works if x is bigger than 0. So what we do is we have to start restricting domains on certain things to make them work. Okay, I want you to try the theorem. There was a part B, wasn't there? Did you have a part B to that one? No, we did that already. I missed part A. Did I miss part A? Why am I? My notes aren't quite. We didn't do that negative 3x cubed plus 1, did we? Oh no, I'm sorry, I'm just ahead. Sometimes these notes are. There we go. We're okay. I just got off topic and I got excited. So steps for finding the equation of inverse. If it's 1-to-1, you have y equals f of x, switch x and y. If possible, rearrange it to get y by itself, because then you can write f inverse. And you can always check by using the theorem. So this is what I want you to try. These two at the bottom on your own. Find the inverse and then check using the theorem for both A and B. I'll put the answers up in a bit. Have first one up there, so you can see did you get the inverse by itself correctly, the cube root of x minus 1 over negative 3. And then I've got the check on the right, so you can see if you did the algebra right there as well. On this next one, there's our inverse, and if you like if I put brackets around there, if you have something like this, does it make sense that you can just flip-flop those things and go right to here? You want to do that? I don't mind that.